Hello everyone, I'm Yang Zhang, a PhD student from Department of Mechanical Engineering at the University of Connecticut. My advisor is Professor Jun Tang. My poster is titled as Fault Identification Using Global Search Enhanced MOPSO Algorithm. This poster is divided into 4 parts. The first part is problem descriptions. The goal of this research is to utilize the piezoelectric actuator to detect the damage in railway track. So here we develop an enhanced optimization algorithm that can handle the large-scale variables in damage identification problem. And then we're using several cases to demonstrate the identification mechanism. So as shown in the figure 1, the piezoelectric transducer is bonded to a metal plate. It can be served as an actuator and sensor simultaneously when the harmonic voltage is applied across the PZT. And then we can use the dynamic signal analyzer to acquire the admittance data. And this data can include the damage information. So as we will know, the fault identification process is an inverse problem. Then we can convert this inverse problem into an optimization problem. Then we can solve it using the developed enhanced multi-objective particle swarm optimization algorithm with global searching ability. And then we can inversely find the damage location and severity. The second part is admittance data. Here we will show how we use the admittance change data to do the damage identification. The expression of admittance change is defined mathematically as delta A equal to S times alpha, where the delta A is called admittance change vector. S is a sensitivity matrix which is obtained using the finite element analysis. Alpha is damage index vector, omega is sweeping frequency, and n is the number of damage. So as shown in the figure 2, there is a peak shifting due to the damage occurrence. But the challenge here is that the shifting data is limited. It means the shifting only happens around the peak frequencies. However, on the other hand, the size of the damage index vector goes up with increasing structural dimension. Therefore, the identification process becomes an underdetermined problem. This is why we had the inverse problem, the definition, in the third part. The simple data points are limited, or it means that the m is far less than n, which indicates the S is a rank-deficient matrix. Then the matrix inversion is avoided here when serving the unknowns. Therefore, the inverse process is converted into an optimization problem. It's mathematically defined as, this is the optimization model. Here in this model, the first objective function is comparison between the admittance changes from finite element analysis and experimental measurements. Because the damage only affects a small area of the structure, so we define the second objective function as the zero norm to determine the sparsity of the damage index vector. The complexity of fault identification problem increases since the size of damage index vector goes up due to the increasing structural dimension, thus resulting in a multimodal optimization problem. The multimodal means the function has a lot of local extremes. So to help the algorithm find the global minima, here we develop several local search strategies to guide the particle in MOPSO algorithm to jump out of the possible local minima. So the flowchart is shown in figure 3 for the proposed algorithm. To guide the particle to select a specific local search strategy, here the Q-learning algorithm is used. So each local search method will be selected based on the maximum Q-table value. In the last part is the results and the discussion. Here we're using two cases to demonstrate the proposed algorithms. The testbed structure is divided into 120 segments for the purpose of fault identification. Two damage cases are studied. The one case with damage severity of 8% stiffness reduction at segment 10 using the simulation data. So another case, the damage severity is 11% at segment 75 using experimental measurements. The identified results are shown in Figure 4. We can see that the algorithm identifies the damage location and severity with a high accuracy for both of cases. And these results just demonstrate accuracy and robustness of the proposed MOPSO algorithm for the piezo admittance-based damage identification in large-scale problem. And this method can be directly applied to the railway track. At the end of this poster, we want to say thanks to the sponsors. This research is supported by the TIDC at the University of Maine and grants from the U.S. Department of Transportation's University Transportation Centers Program. Thank you all. Thanks.